better try the clock since we don't have breaks. Today we're going to talk about one-steppers, one-step algebra. Finally, we're going to get to algebra. That's what this class is all about, algebraic representation. That's some of the goals of the school, is to have you learn algebra, at least a version of it. Why? I think I talked about algebra before, how it's used, where they use it, how the government uses it, right? Did I talk about that? I think I did. How the government probably uses it to estimate how much food supply we need as a growing population. I think I told you the Egyptians first started doing that. They used algebra. That was first recognized, the Egyptians were using it about 5,000 years ago to stock their granaries, to figure out how much food they need with a growing population. The ancient Maya also used it with their symbolic representation. I told you I've been down there, down south, and I've seen how the Maya had lived. I've been in the jungles of Honduras and Guatemala and Mexico, of course. Lots of different things to learn down there, which I really, really love to do. I love the history of math. It's one of my passions. So I know a lot about how our ancestors, not just our ancestors, but ancient civilization ancestors. Our government has taken things, or I shouldn't say, they have borrowed things from different cultures and used it for our technology today. And algebra happens to be one of them. It's mainly Arabic in nature. Most of the algebra we use has Arabic connections, but it has origins that go back to the ancient civilizations. So algebra is used a lot of different things. It's been around for a lot of years. It's multicultural. It's colorful to me. It's my job to make it colorful. Try to. And so to bring in all this extra stuff into a simple algebra class is quite the challenge. But I try to do it as best I can. Some funny cartoons, my excitable personality, and some of the ways I want you to learn through using your brain in multiple ways. Okay? One-step algebra is something that I'm going to take this into steps. Okay? So today we're just going to talk about the one-step algebra. One step means you're doing one thing to it, okay, to this expression, and it's not just an expression, it's an equation. Remember I talked about the difference between an expression and an equation. Anybody remember the difference? This is what we've been working with, expressions up to now. Give me an example of an expression, and then give me another example of an equation.
Expression would be like 2x squared.
So an expression would be something like 2x squared.
Equation would be like 4x squared times.
Let's keep the x squares out of it for now, because we don't do a lot with x squares in here. So let's just make this a 2x, and we'll make this a 2x
plus 10 equals whatever,
we'll say 5. Now this is a two-stepper. I'm going to give you this is a two-step equation. I'm going to give you a one-step, since we're going to talk about one-steps. 2x equals 10. So this is an expression, and this is an equation. So expression versus equation. What's the difference? Equal sign. And another number on the other side, or another expression. So an equation has an expression equal to another expression. This is just an expression. So we just have an expression on the expression side and an expression equal to an expression on the other side. So there's a difference between the two. Now we have some rules we have to abide by. Our government actually uses these rules in our governmental politics. Whether you know it or not, we have this law of equality, right? Everybody should be treated the same, right? You've heard it before. It's sort of the foundation to our government back in the early days, the independence days, okay? So how does that relate to mathematics? Well, that's where it came from. This whole idea of equality was borrowed from ancient Egypt or ancient Europe on the idea of equality. Okay, so the idea is to treat everybody the same. Equations is exactly the same policy. So, but it's expressed here in sort of a rule type of property. And it says that addition property of equality. This is the main rule that allows us to do algebra. Addition and multiplication. Now this is different than our properties we had earlier on. What were those properties? Anybody remember them? What were some of those early properties? Besides the distributive property, we kind of beat that one to death. We had the identity property, right? We had the commutative, and we had the associative, ASOC, and these are all properties of arithmetic, basically, right? Now we have another set of properties that involve equations, and that's where equality comes in. Now let me see if I can regurgitate this for you. It says if A equals B, now A could be anything, any real number, and B could be any real number. So I'm using letter representation first. So if A equals B, then if I add to one side a plus C, I must therefore add to the other side. And that goes with subtraction as well. Even though it's called addition, it also applies to subtraction. Whatever I do to one side, I must do to the other. So if it's adding to both sides, then I add to both sides. If it's subtracting to both sides, then I subtract to both sides. I've got to treat each side with representation of equality. And that's the basic rule for our government. It's the basic rule for our algebra. Without it, you have something that's unbalanced. In this case, will be an equation that's unbalanced. The whole idea is to balance things out. Equality means to balance. Okay? So the whole idea about algebra and equations is to apply these rules. So if A equals B, then if I add or subtract C to both sides, I'm okay. And then it stays balanced. Okay? The same for multiplication and division. So if I have some A or B, A equals B, some term on one side being A, some term on the other being B, then if I add something to one side, it's like a balancing. You've seen those balancing things where if you throw something on one side, it does this, like a seesaw effect, and you throw the same thing, it basically balances out. What if you throw too much on it? Get my robot impression. I'm a product of the 70s. So, okay. All right, so there's my, so if you balance, you have to balance with equality, otherwise the balance is tipped. Okay? All right, so let's do some one-steppers. Let's start with some examples. So what I'm doing really is I'm only covering 7.1 today. The book kind of goes at a different pace. It goes at a much faster pace. So what I'm going to do is I'm going to do all kinds of different kinds. I'm going to sort of set the chapter up, set you up with the chapter, and then next week we'll get heavy duty into it. But for this, and I'm going to give you lots of practice for homework too. Okay? So here's my first example of a one-step. Now, I'm going to start really because a lot of you are going to just guess your way through this. My daughter does the same thing. She wants to say, okay, what plus 2 gives me 5? Well, yeah, you could do it that way. But I want to try to give you a process. And the process is if I see, now this is probably not as, I'm going to rearrange this to say x plus 2. Now, the reason why I changed this to this, I could do that because if you basically, 2 plus x is the same as x plus 2. Remember that commutative property? It said if you whatever you add, you can flip around. Right? So I'm going to do the same thing here. So I'm going to say x plus 2 equals 5. And so the process is to see visualize this as a balancing act first off. Okay? I need to balance this side with this side to make sure they're both the same. And so what I'm going to do is I'm going to look at this plus sign and I'm going to do its opposite to both sides. So I'm going to say subtract 2 to both sides. I'm going to draw this line. I'm going to bring down my x. This turns into a 0. This is an equal sign, and this becomes 3. So my result is x equals 3. Now the beautiful part to algebra, the elegancy to algebra is that you can always check your answers, and you can also, it's ambidextrous. It goes left to right as well as right to left. So some of the things about algebra that I like is it actually goes right to left, left to right. Perfect for somebody who has dyslexia. Okay? So, but the checking process is really beautiful. So you take that 3 and you plug it in here. And you can say 2 plus 3 is equal to 5. So I'm going to expect you guys to start doing some checks. Not every time, but you will.
With these kind of problems in my high school, we were always told, like, we wanted to be X by itself. So that's how we...
Yeah, that's sort of the goal. The goal, and I haven't stated that yet, but I will. The goal is to get the variable by itself, not just X, but to get the variable alone, or isolate. This is the goal of every algebraic equation. 1 step, 2 step, 10 steps, whatever the case may be. Okay? And what you guys are going to start seeing multiple variables too in here, where you have to isolate which variable we're going to get by itself. Okay? So that's easy. Let's do some other ones that are sort of easy. So let's do something like this. Let's get it. Let's look at something like this. Let's say we have -5 equals x minus 2. Now, the goal again is to get the x by itself. So what am I going to do next to the x to have equality on both sides? I'm going to add 2. Why? Why am I going to add 2? Why am I going to add 2? You know, there was a president who used to do that. He used to sign documents with 2 hands. He signed one in Greek and one in Latin. You know what president that was? Could write with both hands. He used to freak everybody out by writing both hands. Exactly the same time. Find out who that was. Put it in your next homework. I'll give you some bonus points. Okay, so if I add 2 to both sides, I get x equals -3. How do I know it's right? Plug it back in. So I got -3 and -2. Is that -5? Damn straight. Yes? You can almost do it, I mean, you can almost do it in your head. Say what? No. Do you see why it's negative? It's a good question. A lot of people are still struggling with this negative positive business. Yeah, you and probably half the class would have put positive. The question is, why is it negative? Adrian?
-5 plus 2. And you take the sign of the bigger number.
Take the sign of the bigger number. 2 different signs means you subtract and take the sign of the larger number. So if you take away the sign, which is larger? Well, 5. And then give it sign. So I think I had a rule about this earlier on. It said, if you're adding or subtracting, you subtract if there are 2 different signs. It's like negative, positive. You're -5 degrees below 0, and it just warmed up 2 degrees. Are you still negative? Yes, you're still negative. But you come up a little bit. Or an elevator problem they can also use. You go down -5, and you come up +2. Well then, if 0's over here, you're still in negative territory. So if you're still struggling with this negative positive business, draw yourself a picture. Get the elevator in. Think about temperature. Okay? These are some of the mnemonic devices I've given you in multiple times. Okay? Use those tools.